Hello, welcome to the 39th lecture of the course. Here also we will talk about Euler-Lagrange equation and see how it can be used to solve examples or to solve to obtain the equation of motion of a given system. It can be a single degree of freedom system or a multi-degree of freedom system. So, this is basically a continuation of the previous lecture. Let us move on to the example. So, let us take the very basic example of a simple pendulum and see whether we can use Euler-Lagrange equation to obtain the equation of motion. So, this is a concentrated mass m, it is suspended by a spring of length L, gravity of G is acting on the body. So, this is a simple pendulum. We have derived the equation of motion of a simple pendulum in the very first few lectures of the course. So, here we will try to do the same thing, but we will use Euler-Lagrange equation and see how easily we can obtain the equation of motion of the pendulum. So, let me write down the Euler-Lagrange equation. So, since this is a single degree of freedom, J is equal to 1, or there will be only one equation of motion. So, this equation can actually be written as, for this particular case, can be written as Now, let us look into the right hand side. The right hand side is equal to 0, because there is no non-conservative force acting on the system. The only force that is acting is the gravitational force, which is a conservative force. The effect of this gravitational force will be seen in the potential energy. So, the right hand side of the equation is equal to 0 for this case. So, this is the equation that I have. So, let me find out the kinetic energy and the potential energy of the simple pendulum. Okay. So, the degree of freedom for the symbol pendulum is theta, or the angle of rotation about the point O. So, if theta is the degree of freedom, let us find out the kinetic energy. The mass of the pendulum is m. So, what is going to be the kinetic energy? The kinetic energy is half m into velocity square. Now, what is u dot? I need to know what is u dot. So, u dot is the tangential displacement of this mass about point O. So, that is equal to L theta. So, if this u is L theta, so u dot therefore is L into theta dot. So, kinetic energy is half m L theta dot square, which is equal to half m L square theta dot square. Now, if I do del t by del theta dot, what do I get? I get m L square theta dot, and then if I do d dt of del t by del theta dot, I get this as m L square theta double dot. Now, let us see into the second part of the equation, which is del L by del theta. So, that is del t minus v by del theta. So, del t by del theta equals to 0, because t is not a function of theta, it is a function of theta dot. So, I have del minus v. So, this is minus del v by del theta. So, let us now see what is the potential energy. So, potential energy V is m g L cos theta, because if this was the if this is the reference, then I have m L cos theta as the potential energy. Therefore, minus del V by del theta is equal to minus m g L sin theta. So, this is one part of the equation and this is the other part of the equation. Now, if I write down the equation of motion, then I have d dt So, therefore, by using the Euler-Lagrange equation, we get the same equation of motion that we have derived earlier using the force balance. So, now let me do another example and see how we can implement Euler-Lagrange equation to obtain the equation of motion. So, this is the problem that we have. So, we have a concentrated spring mass system. So, we have a concentrated spring mass system with mass m1 and spring constant k. Now, on this mass m1, a rigid rod of length L is pin jointed. So, we can say that the 2 degrees of freedom that the system has is, one is this translational degree of freedom, which I call as u, the degree of freedom with which this mass m is going to move horizontally, and as this mass m u move, this rigid rod is free to rotate about this dotted line, and therefore, this theta is another degree of freedom. So, degrees of freedom for this system are u and theta. So, therefore, my u1 is going to be u, and let me call u2 as theta. Now, we will see how to implement Euler-Lagrange equation to derive the equation of motion. Now, to add more complexity, we now include a force So, we now say an externally applied force F act at this end of the rod. So, F is externally applied force. Now, let us see how to find out the equation of motion. So, before finding the equation of motion, as we are aware, we need to find out the kinetic energy and the potential energy. What is the kinetic energy? So, the kinetic energy of mass m1 is half Now, what is the kinetic energy of this rigid rod of mass m2. m2 is going to be half of So, what I have done to find out the kinetic energy of this rigid rod 2, I have taken a small elemental portion dx, and therefore, the mass of this elemental portion is m2 by L into dx. Now, the horizontal velocity displacement is u plus x sin theta. So, I have u plus x sin theta, taking this as the reference. So, and dot of that is the velocity. So, this part is the horizontal velocity. And I have integrated from 0 to L, so as to take into consideration the whole rod L. Now, what is x cos theta? X cos theta is the vertical displacement of the mass. So, this is the vertical velocity. So, now if I write down the equation of write down the expression of the kinetic energy, I can simplify and write it down as so, what I am trying to do is to combine these two and write it in a simpler form. So, if I do so, I am going to get this as half So, this is the expression for the kinetic energy. Of the entire system. So, now let us find out the potential energy. So, the potential energy is going to be half of the spring energy. So, half of k u square plus mg L by m2 g L by 2 cos theta. So, this is going to be the kinetic energy of the system. So, this is going to be the potential energy of the system. Now, therefore, I can say my Lagrangian is T minus V, and I can always implement so, if I implement, let me see what is going to happen. Del T by del U dot. So, let me first do for U1, which is U. So, del T by del U dot is going to be M1 plus M2 into U dot plus so, this is going to be del T by del U. So, d dt of that is going to give me now let us see what is del L by del U. Del L by del U is going to be k into U minus of that. Therefore, the equation of motion for the first degree of freedom is going to be m1 plus m2 into L U double dot plus half m2 theta double dot L plus k u. See, now the right hand side is not equal to 0. The right hand side is equal to the q non-conservative in the direction of u, because this is the equation of motion corresponding to u. Therefore, this in the direction of u. So, that is going to be F, right. So, my right hand side F is the externally applied force in the direction of, so F was applied in this direction. So, it is in the direction of F. So, therefore, we have this as F. So, the equation of motion therefore turns out to be m1 plus m2 u double dot plus half m2 theta double dot L plus k u is equal to F, and that is my equation of motion 1. Similarly, you can do the derivation for the other degree of freedom. So, we can do this, we can find del t by del theta dot, which is going to be half of m2 L u dot plus m2 L cube by 3 theta dot, and then d dt of that is going to give me half m2 L Similarly, my del L by del theta is going to be minus m2 g L by 2 sin theta, and that is going to give me the equation of motion as half m2 L u double dot plus m2 L cube by theta double dot plus m2 g L by 2 sin theta. Now, the right hand side is not going to be equal to 0 again because of this externally applied force F, and we have to take the effect of F in theta direction, which is going to be F L cos theta, the moment that is produced in the tangential direction. So, this gives me the second equation of motion. So, we get two equations of motion corresponding to the two degrees of freedom, that is u and theta. These two equations can also be written in matrix form, and you will see that in this case the mass matrix is non-diagonal while the stiffness matrix is diagonal. So, this is a good example to see that the mass matrix can also be non-diagonal. Now, you will perhaps realize if you try to solve the problem using force balance that it becomes extremely difficult to obtain the equation of motion of this system using a force balance equation. But if we use Euler-Lagrange equation, the finding out the equation of motion becomes rather simple. So, this shows us the benefit of using Euler-Lagrange equation. So, in the next lecture, I will solve another example of slightly more complexity to show how it is easy to use Euler-Lagrange equation to obtain the equation of motion for system of higher complexity. With this, we will end this lecture. Thank you.